This video was produced by Danya, Janice, Jacqueline and Yen. We give permission for this video to be shared for educational purposes with other Part 1 engineering students at the University of Auckland. In this video, we have analysed the cart experiment and our own experiment of a pulley system to explore various dynamics concepts. The aim of this experiment was to find the masses of the cart and the bumper from the data supplied of the two runs. We selected relevant data sections for a series of calculations necessary for estimating the masses of the cart and the bumper. The list on the left depicts the points that we have considered when making a decision on the sections when the cart is being moved by the tension force alone on the x-axis. On the right, there are several assumptions we have made for the calculation of these masses. Position time graphs we extracted from the data of the two runs. This visually represents the displacement of the cart along its track. The peaks represent the moment where the cart encounters the magnetic stopper. The distance the cart is pushed back can be seen through the displacement at the local minimum. This is the velocity time graph we have extracted from both full runs. The velocity increases linearly because the cart is accelerating towards the magnetic stopper with constant acceleration due to the constant tension force. The highlighted gradients on this graph show when the cart is moving to the left, as shown by the positive velocity, and these four sections were used to calculate the average acceleration caused by the tension. These two graphs from each run represent the isolated sections where the net force in the x-axis was entirely due to the tension force. Hence, the gradient of these velocity graphs represents the constant acceleration caused by the tension force. We have selected only these two sections because the data recording ends shortly after the last bounce, meaning that there is not enough data of the cart moving towards the bumper, and this leads to erroneous results in the last section. This acceleration graph shows where the cart is accelerating to the right sharply because of the bumper, and the highlighted sections are where there is constant acceleration to the left from the tension force of the hanging mass. From the four constant acceleration values, we can find the average value to be inserted into the series of equations shown to find the estimated mass of the cart and the bumper, which is 280 to 290 grams. In order to calculate the mass of the bumper, we had to find the average force the bumper applies to the cart. For the simplicity of the calculation, we have carefully selected the data based on where the cart was close to and approaching the bumper. Exploring the forces the bumper applies to the cart, we can find the sum of the forces in the x direction and the tension force. This can be used to find the sum of forces on the bumper, which can then be divided by the acceleration value to calculate the mass of the bumper, around 30 grams, and subsequently the mass of the cart, around 250 grams.
In our second experiment, we have explored a pulley system and relative motion between the two moving masses. To begin our experiment, we made some underlying assumptions. They include that the pulley is weightless and that gravity is the only force acting on the object. The experiment is set up using a wooden board, glue stick, string, extra weight, and two phones. The two phones are of similar mass, so measuring tape was attached to the hanging phone to create an unequal balance. When the hanging weight was released, it accelerated downwards due to gravity, and the tension force on the string has acted through the pulley system to bring the sliding phone up. The experiment was set up so that the sliding mass is connected to the sliding pulley by a fixed cable, while the sliding pulley is connected to the hanging mass through a moving cable and around the fixed pulley.
These are the components of our second experiment. First is the wooden board. It provides a surface for the mass to slide across. There is friction between the board and the mass which must be accounted for in our calculations. Second is the hanging mass. The phones have similar mass, so an additional weight was added to the hanging phone to create a downward acceleration. In this case, we have used a tape measure. Third is the fixed pulley. We have demonstrated a fixed pulley using a glue stick, and we can assume that the friction force between the glue stick and the string is small. Fourth is the moving pulley, which has been looped into the string holding the hanging mass and has a second string at the bottom holding the sliding mass. This pulley will slide up with the sliding mass. Fifth is the sliding mass. For this, we have used another phone.
In our experiment analysis, we explore the following: cable length ratio and its derivatives, Newton's second law of motion, friction coefficients in the system, and relative motion between the two masses.
To derive the acceleration, we have used the ActPy box, which shows acceleration in the x, y, and z direction, which corresponds to the horizontal, vertical, and in and out page planes, respectively. Our experiment focuses on the y direction, as we have assumed that the acceleration of both masses in the x and z direction to be 0. To derive the acceleration, we have found the average acceleration between the highlighted ranges as we can see in the slide.
Based on the kinematic constraints, the total length of the cable is L1 plus L2 equals a constant, such as the length of the cable around a fixed pulley. We can then derive the relationship between the acceleration of the hanging mass, represented as A1, and the sliding mass, represented as A2. This gives us the ratio of 1 to 2. Considering the x and y coordinates of the system and the coordinates of the cable length, the relationship will still remain as A1 plus 2A2 equals 0. As seen from the previous slide where the acceleration of the hanging mass is 1.21 meters per second and sliding mass is 0.67 meters per second, which closely resembles this 1 to 2 ratio. The tension force on the cart can be found by looking at the free body diagram of the hanging mass. The only forces acting on this mass is the weight force and the tension force. As the weight force and the average acceleration is known, we can calculate the tension force, represented as T1, to be 6.02 newtons, and we assume this to be equal throughout the whole cable. Therefore, looking at the free body diagram of the moving pulley, we can see that the tension force from the string holding the sliding mass, represented as T2, is twice that of the tension force in the string holding the hanging mass, which is T1. Hence, T2 is 12.04 newtons. On the left of the screen, we have the friction force graph we can expect from the wooden board and the phone. From a simple experiment where we record the angle at which the phone starts to slide on the wooden board, we can calculate the static friction coefficient to be 0.5774. However, as seen from the kinetic friction coefficient calculated on the right of the main experiment, we can see that this is significantly larger than the static friction coefficient calculated on the left. We can expect this to be because of the additional friction between the glue stick acting as the fixed pulley and the string acting as the sliding cable. Hence, in the middle of the bottom of the slide, we have the calculation of the friction force between the board and the phone when we assume the kinetic friction coefficient is 60% of the static friction coefficient, thus subsequently allowing us to calculate the friction force between the fixed pulley and the sliding cable, which comes to 7.7087 newtons. Then when we consider the fixed pulley's free body diagram, we can calculate the reaction force N using force vectors and cosine rule to calculate the kinetic friction coefficient of the pulley and the cable to be 1.325. From the acceleration values of both masses, we can draw this relative acceleration vector diagram. This allows us to calculate the acceleration of A, the hanging mass, relative to the acceleration of B, the sliding mass, which is 1.817 meters per second. The application of the concepts explored in this experiment can be seen in real life. For example, by understanding the 1 to 2 ratio of the tension forces, we can modify pulley systems to produce infinite number of ratios that will decrease the tension force required to lift a particular mass. In real life, this can be used in cranes where a pulley system allows the workers to lift incredibly heavy construction parts. Furthermore, understanding the friction coefficient is important, as friction must be overcome usually when the aim is to have motion. Lastly, the relative motion is also crucial in many cases. For example, a flying aircraft wanting to travel in a straight line in a windy sky would need to consider its velocity in respect to the velocity of the wind. Thank you for watching our video.